This section is covering 11.7 mathematical induction. It is a joke about a man who believes his wife is hard of hearing. To prove his theory, he stands 15 feet behind his wife while she is cooking dinner and asks what's for dinner. There is no response. He moves 5 feet closer and repeats his question. Still no response. He moves 5 feet closer and again repeats his question. No response. Clearly, he is correct, right? Maybe not. Next, he stands just 2 feet behind her and repeats his question. She turns towards him and says in exasperation, "For the 4th time, fried chicken." Showing something is true for a few values does not prove it is always true. A statement is a sentence or an equation that is either true or false. Statements involving positive integers are common in the study of sequences and series and in other areas of mathematics. Trying to verify these statements can be extremely time-consuming without some sort of an accepted shortcut. Example, 1 squared plus 2 squared plus 3 squared plus ... n squared equals n times n plus 1 times 2n plus 1 over 6 is a statement. And if we would like to prove that it's true, we can create a table and test it for several values of n. So, for example, when n is 1, we see that we plug in 1 for n, and we have the left and the right-hand side of the equation is the same. If we plug in 2 for n, also we find out that the statement is true. If we plug in 3 for n, we do find that the statement is true. 4 for n, statement is true. Do we have to do this for every number to verify the statement? Thankfully, no. Principles of mathematical induction. This is a type of proof that we use in a higher level math courses. So this is a little introductory how we can prove mathematical statements. The principle of mathematical induction includes two steps. We state the first step in mathematical induction is to prove that the statement Sn is true in the first case. S1 must be proved. That is true. The second step is to prove that the truth of Sk implies that the truth of Sk plus 1 for any positive integer k. Note that Sk is not proved true. We assume that Sk is true and show that this assumption leads to the truth of Sk plus 1. Mathematicians agree that these two steps are necessary and sufficient to prove that Sn is true for all positive integers n, and so the principle of mathematical induction is accepted as an axiom of mathematics. Let's use the mathematical induction and then prove the followings. First, we're going to just write S1, Sk, and Sk plus 1, understanding what they mean. S1 just means the first term. Sk means we're replacing n with k, so that means that 2 to the k power minus 1 would equal 1 plus 2 plus ... 2 to the k minus 1 power. The Sk plus 1 will mean, what I should have just said, equal sign, basically, because these are the sum of one term, k term, and k plus one term. Let's make them equal. 2 to the k plus 1. So we replacing k with the k plus 1 minus 1. So we also going to add 2 dot 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 2 to the k plus 1. Should I have to? And we adding one more term. Remember, we're replacing k with the k plus 1, but we have a 1. So overall, it will be 1 plus 2 dot 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 2 to the k, oops, k minus 1 plus 2 to the k. So this is how we would list S1, Sk, and Sk plus 1. For the second example, B, first would be S1, which means 1 is less than 2 to the first power. Sk would be k is less than 2 to the k power. And Sk plus 1 means k plus 1 is less than 2 to the k plus 1 power. So right now we just represented S1, Sk, and is Sk plus 1. In the next section, we will be proving that each of the following statement is true using mathematical induction. So mathematical induction states that first we're going to check for S1. S1 represents only one term, 2, putting 1 in place of n. So 2 does equal 1 times 2, 2 equals 2 is true. Second step is when we assume Sk is true. What does Sk means? We adding 2 plus 4 plus 6 plus dot 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 plus 2k equals k times k plus 1. That's Sk. And we will be proving, if I can make some room. Oh. Fortunately, it's gonna let me. Okay, I will have to erase this and make some room real quick. Okay. Let me add some room. There we go. So in second step, we are assuming Sk is true. So I will move down to the next page so we can have it all together. So for this example, Sk was, let me make sure I have the right problem. 2 plus 4 plus 6 plus dot 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 2k equals k times k plus 1. That would be our Sk, and then we have to prove it for Sk plus 1. So let's set up Sk plus 1. Sk plus 1 is the same as Sk, except, let's write it out, 2 plus 4 plus 6 plus plus 2k plus 2 times k plus 1, that's the extra term. And then on the other side, we plug in k plus 1 instead of k. So we will get that side. If we look at the left-hand side and we understand that this whole section until the very last term is actually the s k plus 1, and we know that that equals to k times k plus 1, we are able to replace this expression with the k times k plus 1. And of course, we have this last term because we are assuming that was true. And then we have k plus 1 times k plus 2. If we prove that the left-hand side and the right-hand side of the equation are the same, then we are done with the proof. If I factor out k plus 1 in the left-hand side, then I will left with k plus 2. K plus 1 times k plus 2 equals k plus 1 times k plus 2. Left and the right-hand side is true. So we are done proving. Let's look at our next example. We will deal with factorials. So first we're going to start with the first plugging 1 in for n. So 1 factorial over 1 plus 1 factorial should equal 1 over 1 plus 1. 1 factorial is 1 over 2 factorial is 2 equals 1/2. So 1/2 does equal 1/2. So we proved it, that first step, that S1 was indeed true. Next, we will assume, I'm going to make a lot of room. Next, we will assume Sk is true. So we'll plug in k instead of n. K plus 1 factorial equals 1 over k plus 1. And then we prove for k plus 1. So we will plug in k plus 1 factorial. K plus 1 factorial equals 1 over k plus 1 plus 1. So let's try to make a rearrangement on the left-hand side to prove it if it's the same. So we have k plus 1 over 1 plus 1 is 2, k plus 2 equals 1 over k plus 2. This is what we would like to prove, that the left and the right-hand side are the same. If we look at the k plus 1 factorial, this means 1 through all the way to k plus 1. So I can break this up as the k factorial, and our last term will be the k plus 1. And the k plus 2 factorial can go all the way up to k plus 1 factorial. And then the k plus 2 is our last term. Remember, we want to prove it that this equals to 1 over k plus 2. So what we recognize is this part on the left-hand side, if we roll back, what was sk was k factorial over k plus 1 factorial can be replaced with the 1 over k plus 1 because we assume that these left and right hand side are equal. So if I replace the highlighted part with the 1 over k plus 1 times k plus 1 over k plus 2 equals 1 over k plus 2, they can recognize that if I simplify the k plus 1 with the k plus 1, I do get 1 over k plus 2 equals 1 over k plus 2 on both sides. So we prove that the statement is true. The last proof will be proving that 2 to the n is greater than n. So we start putting 1 in for n. 2 to the first power is greater than 1. So yes, it is true. Then we're going to assume sk. So 2 to the k is greater than k. And we're going to prove for sk plus 1, which means 2 to the k plus 1 equals k plus 1. We can break the 2 to the k plus 1 as 2 to the k times 2 greater than k plus 1. Again, we assume that 2 to the k is greater than k. So if I replace 2 to the k with a k, which we know that 2 to the k is greater, we could set up 2 to the k times 2. It's greater than 2 times k. That will be greater than k plus 1. And it is true if k is greater than 1. So let's see if it's, for example, k is 2. Let's say k is 2. 2 to the second power is greater than 2 times 2, for example, 4, and 2 plus 1 is just a 3. So we can see this is going to be the greatest, smaller, and smaller. And that's what we wanted to prove. And this is the end of section 11.7.